Hello, we begin with the third section of the course dedicated to the energetic aspects. This section consists of 5 lessons, 4 in which we will develop various concepts, and a last one, the usual one, in which we will apply everything we have learned. We will now study the first lesson of the section, that is the 11th lesson of this course, energy and power associated with a wave, which will have the following development, as we shall see below. Well, we begin by analyzing the energy and power of a wave. Recall that waves, or in waves, do not propagate matter. What propagates is energy based on the perturbation that we are there developing. For example, what happens if we make a brief contribution of energy, as we are going to see in this simulation? With this virtual laboratory, here is a hand that is going to move for a brief moment to provide energy to this little ball. And as we can see, the shape travels, the disturbance travels, the energy travels, and it ends up absorbing the J with its head, but that's the end of the story. The ball on the left has not traveled to the right, it has moved slightly, but the ball that hits J is not the same one with which we started the movement, it is the one at the other end. The matter has not traveled, it has moved, that is, it has oscillated, but it has not traveled. But the energy has. What happens is that, well, we contribute energy, we stop contributing, that energy has been traveling, it has reached J, and the wave is over. It is what is known as a pulse, what we have when there is a brief energy input. How can we get a constant wave? Well, as it seems obvious, by making a constant energy input, a continuous input, as we are going to see in the following laboratory. So, it is a matter of moving the hand, not for a brief instant, but in a contiguous way. In that way, at the end, the wave is established in step J. Now you see it better from a safer place than the one, already because you learn from your experience. And what happens is that the energy continues to travel, but we continue to provide new energy so that it continues to replace, at each point, the energy that is passing by until we reach the end. Where the energy is lost by dissipation when the medium runs out, it passes to another medium, or, in its case, it could be that it is reflected, which we are not going to deal with here. Well then, an important touch is that we're doing continuous energy input, which means inputting energy during or over time. So you have to do it at a certain rate. You have to do some joules per second, and that means watts, power. So a continuous wave needs power supplied. You have to be clear that the power can change from one point to another. That is, we can have circumstances like this that we are going to see in this virtual lab. In this laboratory, we are going to simulate that we have a window with a blind that we can change its opacity. Right now it is opaque. We are going to make it now, for example, absolutely open. Obviously, we are not correctly simulating the speed of light. If I did it, that is, if it was practically instantaneous, at its practically 300,000 kilometers per second, here we do it at a much slower speed so that we can see the process through which it travels. What happens if I fluctuate the transparency of the entrance shutter? Well, if the power supplied does not have a constant value but varies over time, we can see that from one point to another the intensity, that is, if it is lighter or darker, is changing, and at the same point also fluctuates. This point here is now lighter, now it is darker, now it is lighter, but not as bright as at the beginning, and so on. So there are variations. It may seem that this is because we are supplying power at a non-constant rate. However, this is not true. Even if the power input is constant, we can still have power changing from one point to another, as we are going to see in this case, which we may not have stopped to think about, but nevertheless everyone knows about. That of a lamp, I'm going to make it supply a constant power. As already stabilized, the power is being constant. At each point, let's say we are with the same level of dark brightness continuously, but they are not all the same. It is brighter, or we have more light near the bulb than as we move away, then it changes from one point to another. Therefore, to say that the energy of this wave does not seem very appropriate, nor of the power, we have to talk about what happens at this point or what happens at this point. That is, we have to say that it happens in each place, and as in each place there cannot be an energy because it really is an infinitesimal element, it is logical to talk about energy density. How is that energy density expressed? Well, if the wave is one-dimensional, as in the case of springs, we would have to speak of joules per meter of length. In the case of two-dimensional waves, such as waves traveling over the surface of the sea, we would have to speak of joules per square meter of sea propagation surface. In the case of light or sound, which travels in 3 dimensions, we would have to talk about how many joules we have per cubic meter of that medium. And what is the relationship between energy and amplitude? Because at the end of the day, it seems logical to assume that the greater the amplitude, the more energy there is there. If we remember from when the simple harmonic motion of a system with a spring and a weight was analyzed, the mechanical energy was a half of the elastic constant of the spring times the square of the amplitude of the oscillation. That means that if the amplitude is double, the energy is quadruple, that if the amplitude is triple, the energy is 9 times greater. That is, it is not direct proportionality, but squared. Taking into account that each spring has this process, if we have a system formed by 40 consecutive springs, each one of them fulfills this relation, and the total energy, the corresponding sum, also fulfills it. Therefore, what can we conclude? That the energy associated with a wave propagating through a system of springs is proportional to the square of the amplitude. Well, this being justified for a case of springs, we have evidently not demonstrated anything for other types of waves. However, although it will not be justified here, it is a general truth, a general property of waves. For any wave, for any type, the energy or energy density as a factor, as a consequence, is proportional to the square of the amplitude. Let us show here 2 examples. It is clear that these formulas are quite advanced and are not part of the present course. I only put them here for illustrative purposes as an example. In an electromagnetic wave, the energy it has per unit volume, it is a 3-dimensional wave. So the density refers to volumes. It is a half of the dielectric constant of the medium times the square of the amplitude of the electrical component of this oscillation. Square, therefore. In the case of waves, I'm talking about gravity waves, the typical ones. I say this because there is another type of waves that can occur on the surface of a liquid, such as surface waves, which are due to surface tension. Capillary waves is the name they receive. Well, the typical ones on the beach, it is superficial. Therefore, it is energy density per unit area, and the formula is a means of the density of the liquid. So usually water, but why can't we have waves in vodka? Multiplied by the acceleration of gravity, if I had added a water, then we could also apply the formula, and again by the square of the amplitude. It is often forgotten or not taken into account that there is also a reciprocal. Logically, if double amplitude is 4 times more energy, because double energy means square root of 2, 1.414, 2 times more amplitude. The amplitude is proportional to the square root of the energy. Let's see this with an example. A wave of amplitude A that impacts against a dike, and that dike is absorbing the energy of that wave, and therefore it is receiving the structural damage that it has to withstand, and be prepared to withstand that damage, a damage that we are going to say is 3 stars. What happens if it turns out that the amplitude is double if we have double the amplitude? You might think spontaneously that, well, now it will be a 6-star damage, double, but we have already seen that it is not. If the amplitude is double, energy is quadruple, the damage produced by a double high wave is 4 times higher. This goes on and on. Effectively, if we have waves that are 10 times as high, they produce 100 times as much impact. So as you can imagine, the tsunami thing is a little bit of a story. Sometimes it is forgotten that this also has a contribution part, i.e., just as the swell causes or provides energy, it must be contributed to it by a wind. If the first swell, there is a wind, simulated here with the cloud, although evidently the clouds do not blow, is generating that swell, what would it have to be, or what would we need to cause the second one? A swell, a wind that provides twice the energy? No, a wind that brings 4 times more energy. And this is where I end, because we will see it in other lessons of the course. Let's wait here to finish the summary of everything we have seen. I am not going to recite it, you can look at it directly, and this is the end of the lesson. Thank you very much for your attention.